Alright, welcome back everyone. This is the second video of my Mathematics for Machine Learning series. And let's just have a recap of what we did in our in the first video, right? So we covered vectors and matrices, but we've only seen, for just like a short moment, we've only seen representing matrices as the systems of linear equations, right? So we just digressed and went on explaining about matrices and how vectors work. We'll go back to the systems of linear equations example, and this video will mainly focus on how to solve the set of the linear equations. So we let's just so we again set the the matrices here, A, B, C, D, E, F, x0, x1, we just say G, H, right? In this case, you can set A as this matrix, and V, or we can just say X as this vector over here, and then this final vector is B, right? So in algebra 2, oops, no, that should be there. Okay. So in algebra 2, we have seen that in solving these matrices, what we can do is that we can just multiply this side by the inverse of A, right? So that is one key identity in linear algebra, is that an inverse matrix is a matrix such that the original matrix times its inverse is equal to an identity matrix. So what's an identity matrix? In a couple of videos forward, we'll understand how these relate to space transformations. However, in this case, an identity matrix is just a matrix where all the entries are 0 except the diagonals. So it should look something like this, right? You have only the one going downside. And one interesting thing about the identity matrix is that multiply any vector or matrix by the identity matrix, and we get the same vector and the same matrix in return. So I think that's pretty cool. So what this means is, when we multiply both sides by the inverse of this matrix, let's just shorten this expression real quick. So we say the expression is AX equals B. So when we shorten this so this is a shortened expression, right? So then what we can do is multiply both sides by the inverse of A negative 1, and then you get X equals A negative 1 B. Notice how I didn't set B and set the inverse of A on the other side of B. I set it B before the B. This is just to such that the dimensions of this are consistent with the vector. So this is the final equation, right? But this is not always the case, because in a matrix, right, in these kinds of setup, we cannot always guarantee that we have like a 2 by 2 matrix, right? Because there is this one rule of thumb that the minimum amount of matrix for all these vectors to be these input values to be I like to call them non very determined. We can only have these values. Okay, so what I actually scratched that. Basically, what I'm talking about is, for systems of linear equations with two unknown variables, you need at least two equations to get the value. And then for a system linear equation with three unknown variables, you need three equations to determine the unknown variables. That is what I mean. In machine learning and linear algebra in general, we cannot always determine that this matrix the length of this matrix will not always be consistent with this format. So, for example, we can extend this out and just say ax, in this case it will be like ax plus 0 plus bx1 equals g dx 0 plus ex1 equals h, right? But then what we can again do is let's just say qx0 plus yx1 equals, actually not yx1, let's just say tx1 equals p, right? So what we can do is represent all these coefficients of the same matrix here, and then we get a, b, d, e, q, t. But then we get the same thing, right? We just get x0 and then x1, right? And this will give us GHP. The thing is, we cannot determine the inverse of a non-square matrix. What a non-square matrix is that the dimensions are the same. So like the width and the height of the matrix is the same. So if like a square matrix is just is of dimension n by n. So if we can determine the inverse of a matrix, we know that the matrix is a square matrix, so it's n by n. This is not n by n, therefore we cannot determine the inverse of this matrix over here. And what we do in this case is a series of steps that allows us to estimate x0 and x1 or any unknown variable. So for matrix A, and we'll just say n by k, and where the vector we just say x instead of by k by 1, right? So it's a regular column vector, such that B is the dimensions n by 1, the number of equations. In order to solve the equation ax equals b, we must use something called the Moore-Penrose inverse, Moore-Penrose pseudo-inverse. And what this means, and what it states is that in this case, what it states is that x is equal to A transpose A -1 A transpose B. Alright. Now the reason why we call it, only this matrix is the pseudo inverse, and we denote this as A plus equals that. Now in order to solve for x, what we do is that we just say x is A plus B, just denoting the Moore-Penrose. And we face this problem of determining the optimal coefficients, aka weights, to be able to solve our task or problem in machine learning. The issue is that as matrices grow and we get like a bunch of fine-tunable parameters, calculating the inverse grows significantly in time. And the computation time complexity of calculating the inverse is actually not feasible. That is why we kind of stray away from calculating the inverse in machine learning, as we have to deal with these matrices that contain hundreds, if not thousands of columns, especially in these big large language models and other transformer stuff like that. So this is called the Moore-Penrose pseudo-inverse. And this is just a way to solve the systems of linear equations. So the next thing that I'm going to cover is linear independence. So let's say we have the exact same matrix layout, right? You have linear. Let's say you have matrix A. It's in the exact same layout, right? So A, B, C, D, E, F, G, H, I. Right. So what we can do is represent A as entries of vectors, right? Entries of row vectors or column vectors. In this case, we'll just say row vectors. So we just say A0 transpose, because that is a row vector, as A, B, C. A1 transpose is D, E, F. A2 transpose is G, H, I. Right. So when we plug this back in, we get the matrix A is equal to A0 transpose, A1 transpose, A2 transpose. Right. So how we deal with linear independence is that what it means is that none of these matrices are going in the same direction. So you're probably wondering, right? Like, how do we qualify if two vectors are not going in the same direction? Well, we first can determine if they are going in the same direction in the first place. If they're going in the same direction, that means they are. So I'm just going to write this down, right? If any two vectors or more are going in the same direction, they are linearly, we call them dependent. Else, they are linearly independent. So they just span out in different directions. So how we determine this is, remember how previously in vectors, what we did is that we multiply like a scalar by a vector, right? So let's just say you have some kind of scalar quantity alpha, right? Alpha is any real number. Perhaps we can say any real number greater than 0. Okay. So when we multiply a vector by a scalar, the property that stays the same is the angle at which that vector projects. What changes is the magnitude of the vector. So the magnitude of a transformed vector that is multiplied by a scalar is just a transformation of the magnitude itself. However, the angle of theta stays the same. So what we can determine is, if given like any given any integer, we can determine if any of these vectors are just another vector multiplied as a scalar, right? And that's basically how we determine if a bunch of matrices are linearly independent. For example, oops, okay, I hope you get the definition. I'm just going to rub this out. For example, say we have a matrix A is equal to 1, 2, 3, 2, 4, 6. Right. So the matrix A is actually, I'm just going to say 2, 4, 6, 3, 6, 9. Right. So what can we see here, right? So 1, 2, 3 is a matrix, 2, 4, 2, 4, 6 is another matrix, and 3, 6, 9 is the last row matrix. One thing we see here is that all of these matrices are just a scaled up version of this initial matrix here. Or we can say, given like a relative point here, the last row vector is 1.5 times the middle vector, and the last vector is 1/2 of the middle vector. You can say it that way, but if they're not linearly, we can say that this matrix doesn't have linearly independent entries. So what we say is that in like this applies into like a space. What we say is that if it's linear, if like a matrix has a bunch of linear entry, we try to like measure that. We measure it using something called rank. So the rank is basically how much linearly independent vectors, right? So in this case, the rank is 1, because you can only have the maximum is that you can only have like 1, right? However, if all of these are the same, then you can if all these are linearly independent, then they are then the rank is 3. So and also an interesting thing is that you don't always have to represent the linearly independent the vectors of the matrix as only rows, right? You can also represent them as columns as well. Right, and that actually one key property where the number of linearly independent row vectors must equal the number of linearly independent column vectors. I'm going to say number of linearly independent row vecs must equal number of linearly independent so yeah. And one thing is that what we can do is that if a matrix is full rank, we are able to reconstruct the matrix, which is also what the rank means. Rank is basically saying, well, how much addition do we need to be able to reconstruct the matrix again with 2 vectors, right? So remember when I said that summing up 2 vectors doesn't change the dimensions of the vector, right? And so basically what we can do is we can multiply a column vector by a row vector to get a matrix that combines both dimensions of both vectors, right? So in this case, what we can do is that A is 1 by 0 by 0 times. So A is 1 by 0 by 0 times, and do not confuse this with a dot product. We are doing basically matrix multiplication here, because we are multiplying each like in matrix multiplication. So we do like 1 by 0 by 0, 1, 2, 3, plus 0 by 1 by 0 times 2, 4, 6 plus 0 by 0 by 1 times 3, 6, 9. So as you can see here, right, we determined that the rank of this matrix RK A is equal to 3, right? As you can see, we are only able to add this 3 times to each other. Therefore, the sum required is also equal to the rank. Now, a good way of representing this is, let's say you have, sorry, I'll get that a formal way of describing this is, for the rank for A, when we can construct it, it's just the sum of a bunch of matrices, right? Because you know that the dimensions haven't changed. So the dimension in this section, inside the summation, will be equal to the same dimension of A. We recall that the dimension of A is a 3 by 3 matrix, right? So one thing is, well, how do you determine? So, well, you have like some kind of matrix. We'll just say A, and then it's actually not. We can say it's B, A, T, right? This represents it's the vector of A, and B is another vector required, right? So, and maybe then some question will be like, how do you determine N, right? Well, the one way, we know, we're just trying to ask how much times will the summation iterate through. So that is what the N means in this case. So N is equal to the rank of the matrix A. And the minimum value of the matrix A, right? Let's say A is like any matrix that is like N by D, right? Common setup in machine learning, right? We scratch this definition, we just say this definition, okay? So the maximum possible rank of a matrix A is equal to the minimum value of the amount of columns and the amount of rows. Because it should be quite intuitive, right? I mean, you can't have, and because first of all, we define that rank means how much linearly independent row column vectors there are, right? Well, you can't have more linearly independent vectors than there are actual vectors in the matrix. That won't make sense, right? Well, because the amount of vectors for row vector depends on N, and the amount of column vector depends on D, we can't have more row vectors and more column vectors. So the rank of A is at most minimum of N by D, right? So this is one key identity over here. And the next thing that we're going to cover is an interesting type of thing, where it's called, well, hopefully you have understood this. Before I go into I go into null spaces, linear independence is just basically how many vectors are there that aren't like scaled up versions of other vectors in the matrix, and that is with an extended definition is equal to the rank. And we solve the rank using, also I forgot, we solve the rank using something called it's the same from algebra class. I won't cover it as it honestly requires a different video, and there are other bunch of YouTube tutorials online. We can calculate rank using row echelon form and reduced row echelon form, right? Now hopefully these terms ring a bell from algebra 2, and they should, because the resultant matrix is that it should look something like this, right? I mean, you're 1 dot 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 for like row echelon form, and then it's like 1 dot dot dot. And then if like a bunch of these entries are 0, up until the last point before it's 0, right? Let's just say another like 1 over here. The length of this is equal, and the length of the minimum of this is equal to the rank. So RKA. So this is like somewhat of like a more intuitive way of representing and how to like calculate in how to calculate it real time. And we can also calculate these in a reduced row echelon form as well. So hopefully these terms like ring a bell, and hopefully and they're actually put to good use now. So what was I on? Yes. Null spaces. So a simple definition of null spaces is basically which variables of x result in the null being how many values of x result in the null being in the when transformed with matrix. Actually, you know what? I'll just go over it. So I'm just gonna say, I think I'm overcomplicating it. You just have the null space, right? So for this system over here, right, ax equals 0, other than x equals like a 0 vector, which is like how many other vectors exist? That's it. It's just this, like assume you have the equation ax equals 0, right? You're transforming x through a and you're outputting and it shrinks to 0. Other than x being shrinked itself, how many other vectors of x exist? The amount is equal to the null space, and that's basically like the broad and general definition. One thing I really want to talk about is the rank nullity theorem. So we'll just add rank here. The rank nullity theorem states that the rank of a matrix A plus the null space of a matrix A is equal to the minimum possible between n and d, right? And like a good way of thinking about this is like, say, let's go back to our previous example of a bunch of like a reduced row echelon form matrix, right? So like it's 1 something dot dot dot. Sorry, I mean row echelon form matrix 1 dot dot dot, and like a bunch of 0 entries here, right? And let's just assume that d is the n is less than d, right? The length of this section plus the length of this section is equal to n, right? The length of this section is equal to the null space, and the length of this section is equal to the rank, as we discussed before. So in order to calculate the amount of null space, we don't really have to do trial and error and determine actually how many possible x vectors exist just by doing trial and error or some sort of computation. We can just get the REF or the reduced REF and get these values here, right? To get the and determine the length of it to get the null space, the minimum length. This length here, I mean, if this length is greater than this length, I mean, we can discard it and only get the minimum value, as stated in this equation. So that is one thing we should remember. And so this also means that the rank of A is at most this value, and the null space of A is at most this value. And also, so hopefully this is a bit clear, and hopefully this you're able to like juggle your mind with understanding the rank and the null spaces. The next thing that I want to cover are affine transformations. So this is where this is where we actually start going into machine learning territory. Because by far we've just been understanding linear algebra to understand machine learning, but this actually goes into linear algebra in machine learning. So a quick spoiler, a simple setup for a machine learning model is y hat equals wx plus b. Actually, I'm just saying b, right? So you have like a series of values x, right? Wx plus b basically transforms the matrix x into the space into y hat, and we call this an affine transformation. If it looks familiar, it should, because this is just a reinvented version of the linear equation y equals mx plus b. And this is actually a really good setup for being able to determine the best possible values of w and b to be able to optimize your machine learning model. Optimizing w and b given x and given y will be covered in a later video, but this is basically just affine transformations. So I believe that is it for this video. This is linear algebra part 2 for machine learning. And the next video will start going into, according to mathematics for machine learning, the textbook that I mentioned before by Dr. Dyson-Roth. We'll be covering analytic geometry, and part 1 of that. So norms, inner products, and all the fun stuff. All right. Thank you, everyone. Have a nice day.